Hello, this is FlippedHarber for Precalculus. In this video we're going to be talking about polar equations and rectangular equations. Our objectives for this lesson are to convert polar equations into rectangular and to convert rectangular equations into polar. The outline for this video will talk about how we're going to go about converting polar to rectangular and rectangular to polar coordinates. And then we're going to look at actually converting from polar to rectangular equations and converting from rectangular to polar equations. You've seen these equations before. We use these equations to convert polar coordinates to rectangular and rectangular coordinates to polar. So you should break these down again, but realize this is how we're going to change our equations. These are the equations that are going to replace our cosines with x or y's, our sines with x or y's, and our r's with x or y's. So let's take a look at an example where we want to go from a polar equation to a rectangular equation. So r equals 4 sine theta. First thing we want to do is actually multiply by r throughout. Now this is a good idea because it's easier to work with an r sine theta than just a plain old sine theta. So when we can, we like to go ahead and make sure that every sine theta or every cosine theta has an r multiplying it. Now this also does some nice things for us on the other side of the equation. It changes it from an r to an r squared, but that's not really why we're doing this. We multiplied by the r just so that it's r sine theta. So what we'll do on the left side is replace that r squared with x squared plus y squared, which is nice and easy, but again, that's not why we multiplied by the r. On the right side of the equation, we replace the r sine theta with y. That's why we multiplied by r, was so that it's a nice, neat y on the right side of the equation. Now, I'm actually going to be pretty happy if you just get this. I'm going to take this equation a step further because I recognize that x squared plus y squared is a circle. So I'm going to go ahead and go through the process of putting this into a standard form for a circle. Now this isn't always necessary. I just want to go through it this one time. Just a little bit of simplification really. So I'll move the 4y over. And notice that I've grouped the y squared and the 4y. The reason I've grouped it is I'm going to complete the square on that binomial in order to make it look like it's in standard form for a circle. So I complete the square by adding half of the 4 squared. So I'm adding 2 squared inside the parentheses, which means that I have to add the same amount, 4, 2 squared is 4 after all. I want to add that same amount to the right side of the equation. Now that I've completed the square, I can rewrite that stuff in parentheses as y minus 2, the quantity squared. So this is our standard form for a circle. We have our x squared, we have our y squared, they're added, and it equals some number. Okay, let's take a look at another example. Another simple looking equation. We have an r and a sine theta, so we know that this is in polar form. When you're working on your homework, they're going to tell you that it's in polar form, but a pretty safe assumption when you see the r and theta. Again, I'm going to multiply by an r. Now there's a couple reasons to do this in this equation. One is to get the r sine theta. That's why we really do it. But another reason, it gives us that r squared on the other side. Now it does introduce another r on the right side. So we're going to have to look at how to deal with it when that r is not squared and it's not multiplied by a cosine theta or a sine theta. So I go ahead and make my substitutions that you've seen me make already. I replace the r squared with x squared plus y squared. That's nice and direct, very easy. The r sine theta I replace with y. Now because it's just a plain old r that's added to the y value, we need to replace that with the square root of x squared plus y squared. Okay, now simplifying this is not going to get us very far at all. I mean, yes, we have x squareds and plus y squareds on both sides, but the fact that it's added over here on the left, there's not a whole lot I can do. Yes, I can subtract it over, but I can't really combine it with this stuff over here. So you know what? Let's call it good. Let's take a look at another equation. R squared equals sine theta. We want to go ahead and multiply by that r again so that it's an r sine theta. What happens over here on the left side, I kind of have to live with. It's neither good nor bad, it just is. Because I have good things going on over here, I have to kind of live with what goes on over here. Now, my substitution, what I'm going to do here is I'm going to think of that r cubed as r squared times r. So I'm going to make a substitution for the r squared, and I'm going to make a substitution for the r. So what I get is x squared plus y squared, that's the r squared over here on the left side, and the square root of x squared plus y squared is my r. Now on the right side, nice and easy, r sine theta is y. So all I'm going to do is combine these two by adding the powers. I have a power of 1 right here, and this square root is a 1/2 power. So I add the two powers, I have the quantity x squared plus y squared to the 3/2 power equals y. Okay, let's change it up. Let's take a rectangular equation and convert it to a polar equation. So now we're going to be given x's and y's, and we want to make the appropriate substitution in order to make this r's and sine thetas or cosine thetas. But basically r and theta is what we're looking for. So I'm just going to go ahead and replace the x and the y with r cosine theta and r sine theta respectively. I'll do a little bit of combining like terms here. So basically my r times my r gives me r squared. Now again, this next step, maybe it's not so obvious, and honestly, is it really super duper important? No. But I'm going to use a trig identity here. There is a reason we spent that chapter on all those trig identities. What I'm going to do is I'm going to use a 2 from this 4. 2 times cosine theta sine theta is equal to something. What's it equal to? Well, grab your trig identity sheet and try to find 2 cosine theta sine theta. What it's equal to is sine of 2 theta. Now, why is this preferable rather than the top stuff, the stuff above it? Why is sine of 2 theta preferable to cosine theta sine theta? Really, if we can get two trig functions, two trig equations, not equations, but two trig operations down to a single trig operation, that's always preferable. So using a trig identity, we got it from a cosine times a sine down to just a single sine. Okay, let's take a look at another one. Not quite as elegant. You can already see what I'm doing. I've got y squared equals 2x. I make my substitution for the y. I make my substitution for the x. Now notice that this r is not squared. Well, why is this r not squared even though the sine is squared? Well, I divided everything by r. Because I had an r here, I divided the whole equation by r. Notice that this r is gone. Now I could move the cosine theta over by dividing it over. I could change it to a r tangent theta times sine theta. Maybe that'd be preferable, because then I don't have a sine squared over here and a cosine theta over here. Again, I'm not real worried about this. I'm worried about you making the right substitution here, making some good decisions, and then doing a little bit of simplification. You want to do something to try to simplify it. Okay, that's it. So, time to get to work on those problems. I'll see you in class, and I'll see you in line.